So I'm very happy to introduce François Pachet, who is coming from Paris. François is currently in charge of the Sony Computer Science Lab, that is CSL, in Paris. And I met François a long time ago, almost 20 years ago, where we exchanged our career. Is that François, after a PhD, decided to go to the university in Paris 6. And then at the end of the 90s, he moved to Sony Lab, whereas I was in a private company and then decided to go to the university. So we met them a long time ago, and then we have a different career. And so last year or 2 years ago, we met them again, and we said that we should try to do something together. And it was what he's doing is really, really interesting. And I think that there are something which is interesting and appears in computer science now, is that, for instance, when you want to do something, when you want to compute, for instance, the level, when you want to compute an integral or things like that, you can never try to find the exact representation of the function, like mathematicians or physicians are doing, or you can just find an algorithm and with different points try to compute, and so you are focused on the result and not the fact how you obtain the result. And so now we begin to have the same kind of reasoning with the music and the text generation. Is that, for instance, in Google, when you ask a question, you can have a pertinent answer without having, without Google understanding really your question. It's just, so we have some way like that. And so it opens the door to large possibilities for computers. That is, for instance, you are going to see something that I think are a little bit incredible for me about the music and the text generation. And François, it's a pleasure to work with him because as a researcher, he has two things that are really, 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 really nice. The first thing is that he thinks that when you do research, it should be a pleasure. And I think that is very important. And so he always tries to do the thing in a way such that there is a fun somewhere. And so in that way, this is very, very nice. And I really think that if you don't have the fun, you will not have enough energy and enough concentration. It's hard to do some research, but when you have fun, it's better, and some parts that are not really pleasant in the research disappear. And the second part is that François has a great quality, which is not well recognized, is that he's able to invent problems. That is, the question is, so François got an ERC grant, which is a very big grant, but as a researcher, you should ask you the question, what could I do if I got, for instance, tomorrow $3 million, okay, or 3 million euros? And so you need to have some point of view, to have the capability to define some problem, to say, oh, now we should work on that, but it has to be realistic also. And this is one of the advantages of the private company, is that you can do things that are really based on theoretical stuff, but at the end you should be able to show something to the people who pay you, roughly. And so this is something that is very interesting. And I really appreciate him for that. And now I thank him. He's going to speak about music and text generation in the style of.
Thank you very much for your very nice introduction. I don't think I deserve all these compliments, but I will take them anyway. Thanks. First of all, I guess like most of you, I'm basically a computer scientist. As Jean-Charles, as you know, you probably know him very well. He's doing constraint. I also did a little bit of that, and combinatorial optimizations, machine learning. Since I was in Sony, which is actually 18 years ago, I was trying to study various kinds of musical problems. And as Jean-Charles said exactly, I'm indeed quite interested in inventing problems, not just because I'm bored, but because I think it is very important to invent new classes of problems, to also do interesting technology. I'm basically, I like technology like you all, but I was kind of bored at some point to try always to solve the same problems. Anyway, So I'm a computer scientist, I have a PhD in computer science, I have diplomas like most of you, but I have one diploma, which is this thing, which is on the top of my list. And this is like this badge, you know, visitor badge. It's exactly like this. It's a license to play in the Paris metro, so to do what is called busking. And to get this thing is very hard. It's harder than to get a PhD, I think. I mean, in terms of statistically, I mean. You have only you have only 100 per year, and thousands of people try to get this. And to get this, you have to play music in front of some people from RATP. Okay, and it's very hard. It's very, very hard because, you know, I'm a guitarist, so I played jazz, and I was sick that day, and I thought I would not get it. I got it, I was very, very proud of this achievement. But also, I show this because in my research, I always we try to solve problems that really have some meaning somewhere. It doesn't mean that I'm trying to do only applied stuff, because I think in our project currently we do pretty theoretical stuff as well. But as Jean-Charles said, indeed, we try to always go back to the root of the problem. What is exactly the problem? Try, you know, to keep the direction. Anyway, so I'm interested in music. I'm a musician amateur. And I've been always fascinated by the question of how people compose music, how they compose music that I like, actually. Not composing in general, I'm not very interested, but you know, when there is a song you like very much. I'm a boy of the 60s, or the Beatles, you know, Bob Dylan, or whatever you have today, and there is an attraction in there sometimes, and I always wanted to understand that, and from the viewpoint of a computer scientist trying to model it. So, thanks to this ERC grant, I had some money. I decided I could go and see all the people I like, at least all the people who compose music that I like, and ask them, why do I like your music? You know, what is in there? You know, what are the features? You know, I can understand those features, and I can model it, and then I can maybe understand better all that. Recently I discovered that I'm not the only one to be interested in music and constraints, because I will talk about constraints. Recently, this year in April, I think Donald Knuth, whom you know very well, one of the pioneers of computer science, actually gave a talk exactly on that subject. You know, he was composing a piece of music, polyphonic music, and he talks a lot about the constraints and all that, and how composing is basically about trying to satisfy various kinds of constraints. The difficulty being that most of the time, the problem is not so much to solve the problem, is to define the problem. Once you have defined a musical problem, then you can find a solution. So again, as Jean-Charles said, by the way, here again, it's not as simple as that. I mean, the problem is more in the definition of the problem than in actually finding the solution. And in my talk, I wanted to talk about music and text. And interestingly enough, Knuth in his talk is also talking about this very French tradition of writing text or literatures or poetry with constraints. So you have this example of palindromes, which are texts that you can read both ways. Georges Perec, a French writer, wrote a very long one. This is the work we have done actually with Jean-Charles. I think I will have the time to talk about it. Or things like novels in which you have what we call lipogram, where there is lipo means remove, so something is missing, you know, a letter is missing. Like La Disparition is a novel by Perec where there is no single occurrence of letter E, and it's a real novel, you can read it. It's very famous, it was translated in English, it's called The Void. And there is another one he wrote, which I think is even more interesting, called Les Revenantes, with a faute d'orthographe. There is a typo, as you can see. And this is the first sentence of Les Revenantes. Les Revenantes is the opposite of La Disparition. It's a novel, there is only the vowel E, no other vowel. And the first sentence is this one, Tel des chèvres en détresse, cette Mercedes-Benz verte, les fenêtres crêpées, well, and so forth, you can read it. And so why I like very much this example, is that this constraint of having only E is, of course, very artificial. I mean, this is not the way people talk or write. But then you see this Mercedes-Benz. Mercedes-Benz is really nice because in terms of Markov model, where if you are old enough, I think now it's no longer Mercedes-Benz, because I think Mercedes bought Benz completely. But you hear Mercedes, you expect Benz, and then it fits with the constraint. So it's just a way to say that, you know, having constraints is also very often a way to trigger creativity. Trying to find solutions to complex problems is a way to invent new things, sometimes, not all the time. So here I'm interested in this context of how what constraints can we set to define interesting musical problems or text problems, and how to solve them, how to model style, how to understand creativity in those domains. I will skip this. So basically I'm interested in sequences now. Text is a sequence of word or letter. Music is basically sequential also, although sometimes it's not really very clear. But so what you have a corpus, you have a set of finite sequences, and then each sequence is a finite state, is a finite sequence of states or events, notes, chords, you know, things like that. And what we want to do is to generate one sequence out from this corpus that is the best or the most probable, you know, that kind of things. Or you want to generate all the sequences that come from this corpus and satisfy various constraints. So this is kind of optimization problem. Or you want to generate a representative subset of sequences. You know, give me some sequences that are really representative of this corpus, but of course different. It's more related to sampling and to statistical inference. And you want them to enforce some properties. Or if it's a palindrome, you want it to be readable both ways, but it's a very strange constraint. In music, you have many constraints, interesting constraints of that kind. And you want it to sound or to read like, you know, you want it such that if you listen to the sequence or you read it, then it reminds you of the original corpus. This is both a psychological notion, you know, what it sounds like. It's in the end, someone is going to say yes, it sounds like or not. And then it raises a lot of problem of distance. You know, what is the distance between a sequence generated from a corpus and the corpus and other sequences in the corpus? And obviously, the departure from this was Markov chains, because Markov chains basically is exactly what they can do. They can model a set of sequences very well. It's very, very easy to do. And you have this hypothesis, Markov hypothesis, which tells you that the probability of an event, given everything before, depends only on the current event or on the last D event, if you have a Markov model for order D. And this is very easy to estimate. You can estimate by counting frequencies, so it's O of nothing, of n, no cost. And then when you have a Markov model, you can do random walk in that model, and by definition, you will generate sequences that are kind of look like, sound like, whatever you have you had in the first place. And this is how it all started. You can do this with music. I will not go into the details of all the kinds of the species of Markov model. Order 1 is what I said. Order 2, you remember only the two last states. In practice, what people use is a variable order, where at each step you take the prefix, which is the longest one, the prefix bounded by some max value, which allows you to have what is called variable order Markov chains, which are more interesting for a number of reasons. I don't have the time here. But all this is very easy to train and to implement. Even in real time, so this is how I came up with this system continuator. Sorry for those who have seen this millions of times. So the guy is playing, he's improvising here. And the system is building a Markov model of all the transitions here occurring between the notes. And when he stops, playing, there is a random walk starting from the end of what he has played and walking randomly in that model. And of course, the trick is that it will sound indeed quite the same kinds of notes, chords, transitions, and stuff. And the more you play, he will play a bit more. The more you play, the more the model is updated. And the richer it gets, and the more interesting it becomes. And then you can create dialogue like this, which are very, very interesting. So here he's playing, so the system stops playing. And when he will will stop, it will resume, it will continue. And so it works remarkably well. This is why the Markov chains actually are so popular, not because of this system, but in general, because they can capture pretty well the dynamic, the statistics of a complex corpus with a very, very low cost. The same things happen with the children. For 1 hour. Jean-Charles was talking about having fun. Obviously, this guy had some fun. 4 years old, if you play piano, you play 20 seconds in average. If you have a child, you can try, unless he's a genius, you know, but 20 seconds. And with the system, they could play 45 minutes. For at this age, 45 minutes of anything is very improbable. Now, what's interesting is that because of this kind of system, this is why I got interested in these ideas of flow and flow machines and all that. After a while, the guy was bored, and he started to invent things. This is what he played. So this guy has never played piano before. Huh? This is the second day, I think, of the session. This is a session for 1 week. So he does the same kind of things. Perfect, by the way, it's very tonal. Of course, the guy does not know how to play, but he invents himself the notion of ascending and descending arpeggios. He has some idea of tonality. Of course, he does not know how to play, that's not what I'm saying, but he's pushed to invent. He's pushed to do something different because in front of him he has this system constantly pushing back stuff at him. So anyway, Markov models, music works very well. You can do all those kinds of things. But then if you want to go further, you want to compose, you want to arrange, you want to improvise really, like on the jazz score, you want to do accompaniment, well, all these situations, you want to create music for a soundtrack for a movie, then you have to control, you know, what's going on. You cannot do random walk because you have to be sure that certain things are going to be okay, like syntax when you talk, you know, or meaning, you know, stuff like that. And the problem is that it does not work with Markov models, I would say by definition, because a Markov model is based on the hypothesis that you just capture the local interaction, let's say, correlation between events. And so suppose you want to do a phrase in that style. This is John McLaughlin, a guitarist, and you want to end with a very precise note, not just like that arbitrarily, but because this is a F and you are in F minor, F, this is F, it makes sense, for instance, in some situation to end on a very specific note and to start on a very specific note. What do? You do random walk, you have no guarantee that the last note here is going to be F, so you do it again. What do? Maybe there is no solution. Anyway, there is no way to be sure that you do this fast, okay? But however, if you look at jazz, well, I will show you that is exactly what jazz musicians do in real time. So there is there is a trick somewhere. So what is control is what we call unary binary constraints. Like I want the last note to be this, I want the middle note to be that, I want to start by this, I want the C major in the beginning. So localized constraints, max order, I will mention briefly that you want to avoid repeating the corpus too much. You want to avoid plagiarism, you know. So if you have a model of Charlie Parker, well, a very good model is to play back all the Charlie Parker stuff, okay, but this is not what you want because you have a constraint, you want something new, let's say. Meter in music, essential meter is durations. You want the thing to be exactly 16 bars. So the total duration is, you cannot fool around, you cannot do something that is 16.5 bars, you know. So you have to ensure that all the durations sum up correctly. And all diff is just to please Jean-Charles here. You know, all diff for that kind of thing is to ensure that there is some variety in there. 1/f distribution that you may know, very important in nature. You know, a natural phenomenon or a human phenomenon have very often 1/f distribution, so you would like to have also that kind of distribution in the output. How can you do that with a Markov model? Well, basically you cannot. You cannot, because Markov model is not going to guarantee any of these. So what people do usually is generate and test. And so what we have been doing for a couple of years is trying to take all these issues of meter, plagiarism, max order, and distribution spectrum, and try to find what we call Markov constraints. So how can I generate all the sequences given by a Markov model that also satisfy all these constraints? Why? Because I want to control what the system is doing. I want to do real composition. I want to do real improvisation, and so forth. I will not detail all of this. I will just give you a few examples, and mostly of the output, not so much the technique. But the first thing that was interesting we discovered 3-4 years ago is the unary constraint thing is very nice. So this is a guy playing jazz and doing what is called a break. So at some point we will play. He will play alone, and the tempo is going. It's a song called Night in Tunisia. And now it's starting. 1, 2, 3, 4. 1, 2, 3, 4. Stop. And the last note, after the 16 bar, was exactly the root of the tonic of the chord. So he's doing exactly what I said. Saying a 16 bar is 64 notes. The last note is exactly, I don't know if it's a F or C or whatever. So he has a control on the last note, and he's not doing any mistakes, ever, never, never, never. So how can you do that? How can you generate a Markov chain of 64, be sure that, and generate many of them, because it's improvisation, so each time is different, all in that style, that kind of bebop phrases, and all of them have to end on that note, and all the possible phrases you have to generate with your generator. Okay, so this is a sampling problem. And we thought it was hard. Well, it's very hard to play like that, but I mean the problem of generating that sequence seems to be hard, because basically you have to explore the set of all the sequences of length 64, and which is something at the power of 64, so it's not something you can do. Something is the size of the alphabet, is about 20 or something. People are interested in virtuosity. This is how I create. I would like to invent the problem of virtuosity. No one is interested in virtuosos because people think they're just, technocrats. People who are just interested in technique. It's not true, because virtuosos do things that are extremely interesting. So the only people who study virtuoso are the neuroscientists and people doing physiology, especially for drumming. Basically, they say that virtuosos, people who play very fast, they can do it just because they are able to, let's say, liquefy or transfer all the knowledge in the body. So the body is going. They don't think, because if they had to think for each of these nodes, they would not have the time to do it, because that there is a bounded time needed to think about what is the next node to do. So basically, they're very good because they do this. They avoid the speed trap of the cortex. So basically, they don't think. Okay, that's fine. It's very interesting. But I'm interested as a, let's say, AI problem-solving perspective. How do they solve the actual problem of generating a Markov chain with a unary constraint? And so this is why I was interested in virtuoso at some point, because basically they seem to be solving NP-hard problems in real time, so it's quite interesting. And we started to look at that, and we realized that no, actually it's not NP complete at all. And there is a paper describing the solution. So basically you have a Markov model, M, and you have a constraint, unary constraint, that tells you at each position in the sequence you have to have a constraint. This value is forbidden or is a reduced set of values allowed. And then you can build an M prime, which is a non-homogeneous model, such as this model. If you do random walk in there, it generates exactly the sequences of M satisfying all these. And it generates them exactly with the probabilities they have in the original model, which is quite not easy to understand how you can do that. I give you just an example, just so that you have a little bit of technique. You have the corpus is this melody, ta 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 ta, do, ends on C, and then another melody which is the second one also ending on C. So you build a Markov model of this. You have the priors, probabilities. For instance, C has a probability of 1/2. The sum is 1. And the transition probability from C to C, from C to D, okay? And there is nothing from D to D. You can check, okay? Fine. And then the problem is you want to generate 4-note melodies, sequences, from this model such that the last one is a D, for instance. But you want to generate them with the right probabilities. So you don't want to generate them, with equal probabilities. Some of them are more probable than others. So the scheme that we have described here, which is based on the idea of using constraint satisfaction as a way to filter out all the values. So basically the 0 here is going to backpropagate, up to there. And also to retro-normalize the probabilities so that at the end you get different probabilities at each step. You see this one is actually very comparable but different. You had 1/2, now you have a bit more. A bit more or a bit less? A bit more. A bit less. So you see what happens? You put a constraint at the end, it biases all the probabilities slowly and actually decays, of course, but you can do this with any constraint. So what is really nice is that once you have done this, you do random walk in there, and you have a guarantee that you are doing exactly what you want. So you see, it's quite interesting. You have compiled the constraints in the model. So with this, you can build a system called Virtuoso. So I have trained the system with my jazz lines, and I control with the Wii. I can do very fast lines, all synchronized with the constraints of melodies. This is Cantaloupe Island by Herbie Hancock. So I can play very, very fast. Of course, I could not play myself as fast. But this is me playing with my own style, with some binary constraints in real time. Okay. And modulating. The only thing I have to care about is start, stop, and the speed. How many notes per like on a motorbike. And there is a guarantee that it's always right. Okay. So it looked like a hard problem. It was not that hard. It was quite interesting. Actually, recently we discovered that belief propagation techniques can do more or less the same kind of things. So it's not that surprising, but it's interesting to make the link between what they do in statistical physics and this purely constraint-based approach. Now the next problem was much harder, meter. So meter, again, if you don't know anything about music, that's okay. You can understand what's going on. This is a score, and you know that this is I don't know how to say in English, a blanche. So this is a duration of 2 beats, half note, 1 beat, crotchet, quarter note, okay, thanks. So they are all different durations. And in music, there is a rule that everything in one bar has exactly the duration which is written here, which is 4 beats, You don't put 5 beats in the bar. I mean, you don't play it because the beat is the time, so you never fool around with time. And the thing is that, you want to generate a sequence of notes with different duration, but you want exactly, 8 bars, so 32 beats exactly, but they all have different durations, so you can see the problem. This is a Markov sequence, but all the Markov sequences with, 20 notes, they have all different total durations. So how can you enforce that you have a Markov model with stuff with different duration, and then at the end you have exactly the right duration, and also, for instance, you don't have notes crossing bars. You don't have a note that starts here and ends here. Well, you could. I mean, in music it's allowed, huh? But suppose you don't want to do that. How can you enforce it again in the Markov model? You see the problem? You are not going to explore all the possible solutions. So this is an example with Michel Legrand. By the way, I like to take examples in popular music rather than classical music. It makes more sense to me, but it's not because it's popular music that it's simpler. It's actually much more difficult to do a proper Michel Legrand tune than to do a symphony. At least this is what I think in classical music style. And you want the total duration 8 bars, and so the total duration is a sum of duration of each note, okay? And if you don't want any note to cross here, then it means that duration until the note that's before, or the first note of the bar, is also a multiple of 4, for instance. So how can you do that with the Markov model? There is no way. I mean, you can generate and test, you can tweak, you can do bricolage, but And basically, the problem is that even with a very, very simple model, it's very exponential. So for 33 nodes here, well, another problem is that you don't know how many nodes you will have. Because maybe you have only half nodes or only quarter nodes. If you have only quarter nodes, you have 4 times as many nodes. So it's a constraint satisfaction problem in which you have a variable number of variables. It's not very, very nice. And if you explore all the passes given by the Markov model, you have something like 13 million. So 13 million, okay, you could do it. But I mean, you see that it does not scale up. But then, and it's exponential, of course. So you cannot explore that. And then comes Khovansky, who is a mathematician. And there is a very strong theorem that tells you that the sum, what is called a sum set. So you have a set of integer A, and you are interested in the set of all the sums of these integers. And you do H sums. So if H is 2, then you do all sums of 2, sums of 3, sum of 4. This is H. And naively, if you are interested in the cardinality of this, you would think that it's something at the power of H. I mean, naively, if you just try to imagine what's going on. But Khovansky tells you it's a polynomial in A. It's much, much less than what you think. And actually, in practice, it's actually even less, which does not mean anything, I know. But, so, thanks to this guy, we are not going to explore the set of all the passes, but we can explore the set of all the pass durations. The total duration is very small, so you have until 130 pass, but only 3 sums of 3 durations. And 13 million, only 9. So that's okay. So this is the basis of this thing we call the meter constraint with Pierre Roy, which is a constraint in the domain. So it's formulated in the constraint as a global constraint in the jargon of constraint satisfaction. Anyway, so which guarantees you that you will generate all the Markov sequences with a given min and max bound on the total sums and also on the partial sums. So basically, it solves the problem. So this is called pseudo-polynomial. It's not really polynomial, but it's anyway much better than to directly study all the passes. You see, so there is a trick in there which allows you to do this. So thanks to this, okay, you can do meter. So what does it mean? Well, you can do there is, I don't know if you have noticed, but in the example I showed of continuator at the beginning, there is no beat. No one has noticed because it's a magical trick, you know. But there is no beat. For a good reason. I mean, it's impossible to do a Markov chain with the beats for that reason. But now we can do beats. We can do Markov chains with guarantees about the durations. Okay. So what we can do with this is comping. So this is a guy, a jazz pianist, English, and we are interested in how he it's called comping, how he is able to make accompaniments of various jazz musicians. These guys are very, very well known in the UK. And so we record all these guys, we record him. And I just want to show a bit of guitar attachment. So various tunes, various and we record this. Okay? So here you have a beat. Okay, so we have a reference beat. Okay, what do we want then? We want to apply this to new tunes. So this is, for instance, what Ray has played on Girl from Ipanema. This is the original recording. Okay, and this is Giant Steps. I'm sorry, there are examples from jazz. Giant Steps is a very well-known tune in jazz written by Coltrane. This is what you get if you have a basic rendering. Oh, sorry. Oh, no, I cannot. Why I cannot? Okay, I cannot. You cannot hear it. But it goes like da 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 da. Okay, lots of chords, lots of harmony. Really, very different from Girl from Ipanema. So what I want is to have the same accompaniment I have this, but to map it to this, or to twist it so that it fits with that tune. And this is what we get. Well, if you know a bit music, you can see that the beat is perfectly satisfied, but yet the guy is playing. He's not playing very square. He's playing all sorts of stuff, but it's always okay bitwise. And you can see that this video is very long. I can play for literally hours, different stuff, all sounding exactly the same, same kind, same style, and all satisfying that constraint. So this is quite new. It's something that no one could do before with Markov chains, to have enforced those kind of, let's say, called global constraints. Ray was very happy. He says, read great. You can even hear the wrong note. But you see, the trick here is the guy able to recognize himself? This is absolutely crucial. Otherwise, I'm just fooling around with data, So the guy, yes, yeah, it's me. And we did some tests. Sometimes he does not even remember what he has played, and he can be fooled. So this is very important to do it. Well, here you can do this with the same tune, ta 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 ta, with other style. And you see that here. I'm sorry. So here you can recognize the soprano, ta 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 ta, and so forth. But then you can also recognize the Wagnerian thing of the chromaticism, all the notes here which are moving step with a half-tone motion, So the trick is a bit like with people doing image synthesis, is you have a kind of texture and you want to map it onto a kind of structure or kind of constraint. But here, of course, very hard because it's not a continuous data, it's discrete domain, and then you cannot afford any wrong note. All this has to be strictly done with Wagner stuff. By the way, so this is generated from MIDI files of Wagner's tetralogy. So we take the tetralogy with no metadata at all, just take it as a source, build a kind of Markov model, apply the soprano of giant step as a constraint, and get this. I'm not sure I have the time to show this. I will skip this, but I will just tell, sorry, this Ivan Lins is a very, very famous composer in Brazil. He has composed a tune which is one of the most recorded in the history of music. And in particular, he has I will show it anyway, because I like it. Okay. He has recorded, he has played, composed, sorry, this a tune called The Island. In Brazilian, it's called Começar de Novo. I don't know why it's translated as The Island. Start again. And it's a tune with lots of harmonies and chords, which are really nice. Lots of modulation, so people who like harmony like this tune. It's in standard jazz books. Okay, so I went to see him in Rio, and before I had the model of these guys. Do you know Take 6? So Take 6. Oops, it's going to hurt. He's a 6 a cappella. Oh, say does that star-spangled banner yet wave? So there is a reharmonization of the national anthem, the American anthem. And they have a harmonization style which is extremely, extremely nice and very hard to imitate. It's really virtuosos in arranging. So what I did is I got scores of their 10 of their songs, of their arranging, multi-voice, and then I applied it to this song, to Começar de Novo, to The Island, and then I want to see Ivan Lins. So you see, I'm not afraid. And this is in Rio, and I played, it was for an interview. At the end, I said, do you have 5 minutes? I will play you something. So I played this thing. So this is it's not exactly what I played. So the sound is not nice. But it's his song with all the harmonies like Take 6. Okay? Okay, I don't have the time to, but and then this is his reaction. So maybe you're not specialist in harmony, but there are incredible stuff happening in the chords. And of course, only harmonic nerds can appreciate, of course, but I wanted to be sure that he could listen, he could hear them. So this is my validation. And in that project, I'm not doing any cross-validation, whatever. I'm going to see the guy and see what is his reaction. And so I said, yeah, that's okay. And he knows very well, takes it, and okay, this was just for the... Okay, max order, I don't think I have the time. I just mentioned the problem. You know Markov models, probably, you know. And you have the order. So if you have order 1, okay. If you have order 2, order 3, order 4, so the higher the order, the more, if you apply this to a text, the more you will have a tendency to replicate very, very long chunks of the original data. You know that. You have already tried for many reasons of sparsity, actually. And this is something that is very well known. And the problem is that if you increase the order, you have something which is better. You know, it sounds more like English or music, but then it also sounds much more like the original. So what you would like is to have a high order, but not too much plagiarism. So this is what we call the max order. So you want to have a high mean order, but you have a very low max order so that you don't replicate chunks of the corpus. Otherwise, you are not doing anything new. This is a slide that shows how the max order actually is exponential with the order of Markov and different other models that we are studying. And so this is order 1 sequence generated from Eugène Onegin, which is a text on which Markov worked initially to invent Markov chains, you know. And you see order 1, you can have phrases with up to 7 letters or words in a row which are replicated. So it's a lot, you know. So what you would like to is to have a Markov chain where you impose a limit on that maximum substring, you know. It turned out that this problem is very hard. It's not something you can do like this. And here we did a very interesting work with one of the students, with Alexandre Papadopoulos, basically trying to put together the works of regular language done in constraint satisfaction, together with these kind of ideas of Markov constraint. And we came up with a solution I will not describe here, which consists basically building a very large automaton, but then you reuse it for propagation of the Markov constraint. And with this, you have a solution with a guarantee. So you can generate lead sheets or text with a guaranteed max order. So why is this all important? Well, because if you want to create new music, you know, if you create a music and in which there is 1 hour, there is 2 minutes inside your tune, which is exactly Girl from Ipanema, you will have problems with the right holders, and you are not creating anything new. So you want to say, okay, I want something, but I want this maximum, you know, replication boundary. And this is exactly what this constraint is doing, with a guarantee that you have actually all the solutions. And now, recently, we came up with a new result that we have not only all the solutions, but we have them also with the right probabilities. So we are able basically to mix together the ideas of hard constraint satisfaction, global properties on force, but keeping the original probabilities. Okay, I'm doing lead sheets also. Lead sheet is this kind of thing, you know. It's a melody with chord labels here. So this is a waltz in the style of Bill Evans, using these techniques. I would just try to stop it before the end. Okay, here what you can see, all the colors are the chunks that were taken from the original songs and put together. So you can see exactly what the system has been doing, and you can control with max order the maximum size of this, you know, basically. And you have a guarantee of all solutions in polynomial time, which means that you can have an editor now, which is this one, which will be out next month online editor. It doesn't work very well. This is a bugged version, but I'm just showing this to you. So you take a song, take Solar by Miles Davis. This is online. Huh? You remove everything but the first bar, for instance, and you say, I want to do something new. I want to put a G7 at the end, you know, this chord. And then please find a solution. I want Miles Davis. Oh, by the way, it was very fast, but here you had a whole long list of composers. So this is a solution in the style of Miles Davis himself. But you could have taken anyone else. And then you say, okay. Oh, okay. Oh, I don't like that, okay? So you stop, you remove it. And you keep the beginning, so you have more. All these are basically unary constraints, not really, but and then you start again. So this is why you sometimes you want one solution, the best solution, or many solutions, because you don't know really. I mean, you are in a context where you are not able to specify all the criteria, and you can do it again and again. So basically, with those tools, you can navigate in the style, in the space of all the solution in a given style. It was very fast, but you didn't see maybe here, but here we have a database with all the jazz scores and all the scores in Brazilian music, about 10,000 scores. So we can really have a complete representation of all these composers. We have all the Miles Davis, all the Michel Legrand and Tom Jobim and all that, and so forth. Okay, I want to keep a little bit of time about that. Again, Jean-Charles said really rightfully, don't lose the goal, you know. The goal is music. My goal is not only to publish paper at each guy and stuff. I mean, it's fun, but it's not a lot of fun actually, but it's to produce music. What you have heard so far is not music, except at the beginning when I show real videos. What I have shown are scores played by synthesizers, you know. But this is nice for research, but this is not music. So I'm going to play you, this is a lounge, you know, lounge, a style lounge. Music you hear when you go to the Buddha bar, you know. So this is the exact transcription of a tune, of a lounge tune. I'm going to play it as exactly what you hear when you have Pro Tools in your editor, you know, with the sounds onboard synthesizer. You get this. Okay? It's very repetitive. It's not very interesting, but you can see what you get. Now this is the tune you have actually produced. It's extremely different. It's not louder only. The sounds are different, the texture are different, the effect is completely different. It's completely different. Another example, a few examples, just to insist on that. Okay? This is the actual stuff used at the beginning to create this. What is the relation? So maybe you change 10% of the notes here, it doesn't change anything at the end. Maybe you change the reverb here and change everything, you know. So what I'm saying here is that music is not just a score. It's a complex object where you have a score, you have what is called production, you know, the sound, the effects, the compression, the equalization, all these things. And they are actually as important than everything else, sometimes even more. Well, we don't know. But all these Markov models, you know, they are good for dealing with symbolic stuff. But as soon as you go into production, it's another world. The guy is going to take your thing and then do all sorts of manipulations. And the success, or at least the interest that it can raise, is going to depend heavily on this production phase. Sometimes even more than on the initial composition. You know, I have a personal experience of that, where people come with a very great song, you know, and then they go to what is called a réalisateur, and the guy is going to change completely. And in fact, you can really ask the question, where is the original thing at the end, you know? So we have been incredibly interested in audio, not doing only symbolic stuff, but audio, working directly on the sound, the waveform. Although, of course, you cannot do the same things with a waveform, with a signal, than you can do with symbols, as you know very well. But still, you can do various things. So recently, I was asked by the European Commission, the RC, to produce, so you know Ode to Joy, l'Ode à la Joie? So this is a Beethoven 6th Symphony. You know that this is a national, this is the anthem of Europe. So they have asked me to reharmonize it. For the European Parliament, it's mid-June, in various styles. And I said yes, which I think was a mistake. But because it's going to be played at the European Parliament with the Junkers and all these guys. So what is the idea? So you take do you know Prior and C? You know this song? You know this? I didn't know, my daughter knows. here is not a Markov sequence of symbols. You have at least 4 tracks simultaneous, lots of stuff going on. So we have to find a way to adapt all these ideas to real stuff. Otherwise, the MIDI you get here is absolutely not interesting. So you know the Beatles? This is a good joke.
Penny Lane, there is a barber shop.
So. And so forth. And so forth. This is really not completely finished. And then you know this one? By the way, this is 3/4. This is a waltz. 1, 2, 3, 1, 2, 3, and all la joie is 4. So here you have to do some trick. Okay, you get the idea. And so we will do it also in Brazil. Bossa Nova style. How much time do you have? I don't have any more time. A few minutes? Yeah, so fun again. I've been always a Brazilian guitarist. I've done tutorials on Brazilian guitar. You can find it on YouTube. It's a genre I like very much. It's very interesting. So I wanted to capture this. It's very interesting Brazilian guitar because it's very, very diverse. You have lots of, it's not only bossa nova, you know, you have hundreds. We have estimated about 500 different kinds of Brazil guitar accompaniment, like bossa nova is one of them. There are many, many others. And it's very hard to do, to learn, I mean, to play, because it's not, you know, it's not like lounge, it's not like this. You have lots of anticipation, playing before the beat, do all sorts of tricks also with harmony and rhythm and all that. So I went to Brazil. I have a project there where I record some musicians. Like this one is Geber. And I try I record and I want to retain all the specifics, you know, the noise, even the errors or the kind of chord he's going to use. So here he's playing one song, I don't remember which one. We give the lead sheet. And then he's playing his way. Okay? And then this is Girl from Ipanema. You can recognize, but this is generated by the system from his style, and he never played this song before. And so he's trying to listen to see whether it's really him or not. He's trying to recognize himself. Time to go into details, but he plays in a very, very specific way with lots of retardant delays, you know. He doesn't play on the beat, plays a bit, you know, late. And you want to keep that. Of course, if you cut things like this, it's not going to work because you are going to quantize. So you have to do all sorts of tricks here to preserve it. So what you get in the end is this. So this is Insensates, played by him. You know this song probably? By Tom Jobim. It's very well known bossa nova. And you hear behind, it's quite non-trivial what's going on in terms of guitar. So we recorded, and then this is Blue and Green, this is jazz. A jazz tune, which has nothing to do, and you can recognize, I mean, you can do tests, but you can see that it's going to recognize his chords, his rhythm, and all that. Just throwing this one I like very much. This is a song by Paul McCartney, Friends to Go, guitar, acoustic guitar. The melody is just MIDI melody. Okay, it's called guitar strumming, you know. Actually not very easy to do because you have to do really a little bit anticipation. And then you can play All of Me, for instance. There is no seamless. It's exactly as if it had played it. Okay, last example because I like it. I like this guy Benoît Carré. In France, he created this a group called Lily Cube, Voyage en Italie, for those who know this song. And he did a song which I like very much. This one. Okay, and I like the guitar, the electric guitar, okay? With a bit of saturation, you know, that kind of song, arpeggios. So this is what I take. And I can do Michel by the Beatles. And here in this case, there is no cheat. It's exactly, I give the lead sheet, that's all I do. I don't cheat with the original. Okay, so you get the idea. I wanted to talk about text, but I don't think I have the time, unless you really insist. So I suggest I skip. I just wanted to say that everything we did on music, we can do with text. For instance, we can generate lyrics. So this is yesterday, the lyrics this time, by the Beatles. And in lyrics, you have also meter, prosody, I mean, and rhymes. Rhymes, what is rhyme? Well, a unary constraint on the last event. Fine, we know how to do that. So we can take the rhyme structure, the prosody, the meter, strong, weak, strong. Yesterday is strong, weak, strong, and so forth. And take Bob Dylan. So you have yesterday, all my troubles seem so far away. Here to stay. Okay, and this is real time, and I get all the solution I can do with Bob Dylan. So this is the tricky question. Why are you sure it's Bob Dylan? Well, yes, but I would need to do some tests. But you can see things reoccurring. You can do for Beach Boys, Summer, AC/DC, Johnny Cash. Okay, and we did very interesting work with Jean-Charles about palindromes. It's a bit a miracle that we finally came up with an algorithm which is actually linear. No? We spent how much? 6 months? Tried everything, and at the end, Alexandre got a very nice idea. There is a paper at next each guy. So we can generate these things. Let me just give you the examples. Palindromes can read both ways. So you start from a corpus of n-grams, like the Bible or Winston Churchill's, whatever. And you try to build those phrases and use Google n-grams when you don't find solutions. And you see some of them are quite nice in all languages. And we can invent palindrome on one language on the one side and another one in the other way, in any language. And we are having fun with this. This is a bit a kind of having fun. We don't know really why, because, I mean, who cares about palindromes? Apart from that, that is really hard to do. Try to do one yourself, you will see. Even a small one is extremely difficult. The reason it's difficult is, this is what I think Jean-Charles was also interested, is basically because you have two levels, the letters and the word levels. You have two levels at the same time. And it's really, this is what makes it really hard. It's not only a constraint that last equal a is equal n minus a. It's more difficult than that. Anyway, so we did this. Conclusion. What I like to know to say that style is a very is not very tangible, very clear notion, but still it's a bit like a texture, in computer graphics, and I think so the program here is to turn style into a computational object, an object that the machine can build, store, manipulate, exchange, distribute, combine, multiply. There is an algebra of style. You can say, I want this style, but then with a bit of this and a bit of that, minus this one. I want in the style of Top Jobim, but remove everything that sounds too much like Miles Davis. That kind of things. So you have an algebra of style to do this. We currently now, with all these ideas, we can think about style as a computational object. It's a very interesting idea, not only to have fun, but also because I think there is, first of all, a lot of very nice new problems, again, as Jean-Charles said. I try to give examples. There are many, many more, but they are more or less related to sampling with sampling statistical models under global constraints. Already global constraint is difficult, and this is difficult, but doing both of them together actually creates new interesting problems and new ideas. Very interesting combination of ideas from these three domains, combinatorial optimization, machine learning, and statistical inference, which is extremely, by the way, promising. The last thing I want to say that, yes, there are applications, because you asked the question. Why? Well, recently I have a friend, he's like me, he's a busker, you know, busker. He plays outside in the metro. He was in Paris, he's American. He plays very well, guitar and sax, and he sings also. Very, very good musician. And he went to New York last year. And in New York, he plays in clubs, he plays in everywhere, but he also plays in the street. He likes it, you know. Sometimes in Paris, he could make quite a lot of money. Almost as much as you as a researcher sometimes per day. But then recently he discovered that when he is busking, and there is a beggar, you know, beggar, a mendiant, just near, in average, the guy gets 2 or 3 times more money than him. And so on Facebook there is a very interesting debate. Why? I mean, this guy is a very, very good musician. He is really good. I mean, he's not just playing like, you know, no, he's really good. And this guy is doing nothing, just saying, please give me money, gets more money. So there is a nice debate on that. But I think my opinion is that music has no commercial value anymore. It does not, it's worth nothing. Not as an artistic object, as a commercial object. It's free. I mean, you can have music for free, or it's almost free. No one wants to pay really or to buy one song, you know. And it's well known, all the musicians, they have a very hard time now living, not only jazz, in general, pop, rock, everything. Unless you're a superstar, you don't make any more money. You used to make a lot of money in the 80s, you know, because you could sell CDs, basically. But now it's very different. So what has value? Well, style. So the idea that if style is a computational object that you can sell, many people are ready to buy the style of Paul McCartney, melodic invention, the style of Morricone, orchestrations, to do your thing or to do something else, or to do, you know, to do your own creation, but with the style of someone else. And this occurs in many domains. This is what I'm trying to say. Melodic invention, harmonization, orchestration, accompaniment, also synchronization. There is a business also today which is working for music, which is what is called music synchronization. That is music for ads, music for video games, or music for movies. And there is quite a lot of money there. And so all these things, what is it about? It's about a style. You know, people say, okay, I have a movie and I want something that sounds like Ennio Morricone in that scene. You know, this is what they want. And of course, you cannot go and see Ennio Morricone because it's too expensive. But this is what they want, and I think this is a future of not only of music, but also of text generation. You know, so when you write a mail currently, you write a mail, each letter by letter in principle, but this is not what you want to do. I mean, you always write the same, we always write the same mails, basically. You know, we use the same words, the same expressions, the same structure of the mail, I mean, very often. This is something that can be learned, and then it's something that you imagine writing mails not twice as fast, but 10 times or 100 times faster, because you have everything with those tools to navigate in the space of all the phrases you could write about a subject, you know. Of course, this is a bit controversial for text, because in text there is this thing called meaning. I'm very well aware of that. But the experiment we do here is that when you constrain things sufficiently, you can actually generate meaning by very, very superficial and, let's say, low-level devices, like cardinality, imposing words, imposing semantic clusters, and things like that. Anyway, so these are the ideas that are behind the project. I think that it's quite interesting in general, even if you are not convinced by the potential applications. But here you have lots of very, very interesting problems. Again, at the frontier of combinatorial optimization and machine learning. Thanks. I'm sorry, I think I was a bit too long.
In your talk, you seem to give a lot of meaning to time. And this for the Markov chains, for example, you're talking about what is going to happen next. But time is only one dimension, so you could decide that you want to use your Markov chains to say what is going to happen at the next place, but not in the next event of time. Or you could have a dimension that is skewed between time and space. And then you would have another way of looking at future, and the future might not be the next place here, but it would be the next place on the left or something like that. And then you might want to have another way of seeing things. Like when you look at a function, if you look at polynomials, you could look at the coefficients, but you could also look at their coefficients in another basis. So have you explored this kind of thing?
Yes, yes, absolutely. I'm trying to find a slide. Anyway, Markov models are probably the simplest possible graphical models. And indeed, they are based on a binary adjacent relation. So you look at what is next. Maybe NRE, the n plus 1. But, now we are exploring max entropy models in which you can have binary relation, but not necessarily between the next, between quite far away events, not only in time. But you talk about space, I don't know what you mean by space, but when you do multi-voice music, where you have different melodies, there is a vertical dimension, and this is obviously not a Markov chain, because you cannot decide that there is going to be like that. So in that case, you need graphical models which are more sophisticated, and indeed you are completely right. The time is not the most important dimension. What you want to capture is local interaction between stuff, between events, between nodes. So I had slides actually exactly about that, about this thing we are doing currently, which are very, very promising, using those models to model music. But in the end, you have exactly the same issue that I presented here. Meter, for instance. Meter is about sums of durations. And when you have polyphonic music, it's even more difficult because you have sums which are not the same, it's not synchronized, and yet it works. When you have a fugue, for instance, or even something simpler than a fugue, a canon cancrisant, like Bach, it's a line that you can play both ways, and you play together, it sounds well, So in those cases, Markov models are obviously not adapted. So the current line of research we do is to redo everything we have done, but try to use more sophisticated graphical models, like max entropy, where you have indeed arbitrary relations between events, let's say, in our domain. It's a work in progress. And apparently this has been done a lot in biology and never in music. So, but again, I mean, why we are actually doing what you suggest is precisely because we had the problem. At some point we had to generate actually polyphonic music, or we had the problem where the old model does not work. Otherwise, we would never had looked at it. So basically, we are really driven by problems more than by technological ideas.
Are there composers that are interested in what you are developing?
So we work with different composers as they try to use the system. They try to give us ideas what's important or not. We work with Benoît Carré in France. I work with an English composer in the UK, and also in Brazil. I'm not going to work with very well-known people because it's very difficult to do for many reasons. But yes, of course, the goal is to be useful at some point, And what is nice when you work with real people that tell you, well, I don't care about all your great, what I want is, I don't know, to have this interval at that place, and you say, yeah, but it's very easy problem to solve, but we did not, we didn't think about it, we didn't do it, so the guy is going to be stuck for a stupid reason. And so we try to find a good compromise between, trying to explore those ideas of constraints and statistical models, at the same time do stuff that people can actually use for, to produce things. So in my project, which is a ERC project, which is still 2 years, I have promised that I would release three, if possible, three CDs, music CDs, which are produced as a normal music CD. I have some here, I've already produced one. And so the goal is not to do demonstration, it's to do actual music, to publish it, and to look for critics, people who say, yeah, it's good, it's not good, or whatever, that kind of thing. So in the end, yes, we have to do it by definition. I'm not interested in doing demonstrations, really. In the end, I would like to do a song or a CD that's people like, and then say, okay, this CD was created with this technology at that point, and so forth, and try to map it, to ground it, let's say, in the real world.
Yeah, you've mentioned and you have showed how the producing process is making things very different.
Yes.
and how it is difficult to grab it, to collect it, and to apply it to your system. Wouldn't it be interesting to work with people, not only composers, but also producers? And actually, I feel like actually in the music, currently in the music, the producers, or composers and producers, are becoming the real stars.
Yeah,
like Pharrell Williams or Nile Rodgers. If working with these guys, they could maybe help to put in the system what's missing with the producing.
Absolutely, this is what we do. We have a guy in the team who is a sound engineer, and we are building currently a system which is basically an online mixer. I mean, an online, so it's just a web service where you send files and you send specifications of effects and all that. And we try to learn, using machine learning, where to apply which effects to which part, to learn all the interactions between all that. So this is a domain called more or less automatic mixing. The question of you have raw data, raw audio, and you want to put it together. And this is what sound engineers do, and also the mastering, which is kind of a mysterious thing. And it's a domain which is currently only starting to be studied, with, let's say, systematically with computer science tools. There are lots of sound engineering is not at all rational domain. People say crazy stuff, it's like a religion. But now it's changing progressively, because people are starting to do things in a kind of systematic way, discovering that no, it's not true that people think that in pop you should do this, you have to do that. No, you can do different things. So we are doing a lot of work in that area. We have some papers if you're interested. And of course, and indeed the goal in the end is to produce, is to generate a produced object, not only a score, absolutely.
And just back on your answer, you mentioned machine learning to grab the patterns.
Yes.
Are you considering of mixing or like hybridation between your Markov model approach?
Yes, yes. Machine learning in order to generate new mix, of course. Yes.
What about the issue of intellectual property? Because your tools could be used to define what is style from a composer, and to impose and to introduce litigation about the styles, and that is the owner. And so
yeah,
what do you think about that?
Yeah, of course. Yes, because we are trying to create a spin-off, so we will have to handle this issue. So we talk a lot with lawyers. It's very style, as you said, is not defined. There is no definition of style. But the tricky bit is that when you sign a contract with a musician, nothing is written about that. It's written what you can do with the recording. If you have phonographic rights, if you have publishing rights, what can you do with the score? Period. And here we do, we do all sorts of various. So I think my opinion is that this is a domain which is very new. The status of the jurisdiction is going to evolve a lot in the coming years, especially in terms of contracts. So in the project in the ERC, there is something called POC, proof of concept. So I got that grant too. And so we are trying to build new templates for contracts with artists that take into account all these things. So for instance, I record a guitarist, and I will generate things in which I have taken bits and pieces of his recording, maybe transform and all that. So how does it work? So we try to build new contract types that give them, rights, that give them royalties, that also allow the industry to work. This is I think it's basically a no man's land. So, and the way it works today is you have trials. When there is a problem, there is a trial. There are very often trials. Someone say, "Oh, this guy has stolen my song," So what happens? There is a trial. They have those specialists. They come, they listen. Some of them, they count how many notes in a row. So they do max order analysis, basically. Oh, there is 5 notes in a row here and 6 there. So therefore, I argue that this is a plagiarism. And then another guy said, well, no, because here, there is the bass is different. So there is no, there is no definition of what is exactly plagiarism. It's going to be decided by humans. So all this, I think, really the beginning is going to change, I think, a lot now. Because this is also what musicians want to do now, most of them.
Maybe I missed it, but when you create, for instance, Michelle or a girl from Panama in another composer style, so you learn both both songs or both their style, or just learn the actual and then just
I learned the accompaniment, so there is a source lead sheet, a source song, and a recording of an accompaniment. And then I have a target song which is different, and I want to generate a new accompaniment for the target song. So the source song, the target song, they are given.
Okay.
Or you can create them if you want on the editor. I'm just doing the transformation or the generation of the accompaniment.
Okay. And I have another question. Following the first comment on space-time modeling, do you think it will be interesting to model the relationship between the different tracks? I mean, different like the drum and the guitar and the bass. For instance, if once the drum hits that note, then the guitar does something like that.
So I have a student currently doing his master internship exactly on that. So he's analyzing the multi-tracks from the lounge. So we have 100, trying to see what are the rules exactly, you know, between the bass drum, snare drum, bass.
Maybe there isn't, but...
Yeah, so far we didn't find anything, but it doesn't mean that there isn't. No, but what is really interesting is that if you are a musician, you know how important it is, you know? The bass drum, the snare drum, and the bass, very important that it goes together. No one is able to tell you what it means, because, you know, sometimes it means together, sometimes it means no syncopated. So it's exactly a new problem, you know? What is groove, you know? How do you model it?
Yeah.
Because no one knows how to define it, but if you play something, everyone will say, oh, this is right, this is wrong. There is a unanimity, you know. But no one is able to say what is the thing.
And my last story, what was the reaction from the composers actually when you played them? So they were afraid of that it was going to maybe sometimes take their place, or they were happy that there will be new ideas coming from that.
So Miles Davis is dead, Tom Jobim is dead, and Bill Evans is dead. So all the examples of composition I've given, so I did not do what you say. Okay. For composition, I did it for orchestration. Okay. And yes, I mean, probably some of them will not be happy, some of them are interested. As usual, you know, the technology, but I try to pick up the people who are really able. I don't think it's a big issue really, but
question.
When you talked about text, you said there was one tricky part of text, which was meaning. Isn't there meaning in music too? Well, the composer.
What time is it? How much time is it going to? So I'm not a specialist of semantics and all that, and I try really to avoid. You know, it's like. But I think people agree in musicology or computer music to say that there is no meaning in the sense of an external reference, you know. Like there is probably with language where you talk about something, there is a mapping, like in denotational semantics. So in music, people agree to say that the meaning is completely internal. So the meaning is made by relations within the piece, in the sense that there is something repeated or transformed, or, you know. So there are, of course, there is a web of interrelations between elements and stuff inside the piece, but there is no meaning in the sense of external references. And so in fact it means that there is some structure in there, you know, as an object, and you don't need an outside world to describe the structure. And there is structure because somehow all this is probably a kind of complex system going on. I mean, so there is, for instance, a very interesting where I could not talk about it, but there is a paper for also next Ichkai about 1/f distributions. You know, so this has been studied since the 19th century. You know, observed that in natural noise, in some noise sequences, there is a distribution of the in 1/f, which meaning that there is a 1/f relation between the spectrum and its and the frequency. And it also was shown that it was also true in symbolic music, in scores. So, and people say that 1/f is a sign of a complex system, you know, at work. Although it's not very clear, but at least we can try to reproduce 1/f. And the idea is that if you reproduce 1/f, you will create those kinds of structure. though not in an explicit way. You will not say, I want this thing to be similar to this and this thing to be different, but if you have a 1 over f distribution, you will tend to have more structured stuff, things that repeat, and although it's very hard to say what is structured, but the basic idea is to find universal laws that you can infer from the corpus and try to reapply them at the end. So again, I have the same problem that I have a statistical model. I want to generate, to sample it, but I want to enforce global constraints like spectrum and stuff and things like that.
Okay.
Well, for text, it does not answer your question, of course. It's only for music.
So this question is kind of related to meaning, because a song, or a small song, or a larger, or a symphony, every song tells a story, and there's a beginning, middle, maybe a bridge, an ending, and style and composer styles to reflect that sequence. And I'm not talking about the note sequence. I'm actually talking about the sequence of events in a song. So, are you able to reproduce a larger scale of sequence of events? Have your song have an introduction, a beginning, maybe a middle, or it's not really defined, but it should have some external structure. Are you able to do that?
No, it's a very important question. We try two things. Yeah, we are working on that. There is a submitted paper at the next CP conference, by the way, on Allen meter. So it's basically to try to say things like, I want to generate 8 bars, like Markov constraint, meter, whatever, and I want the first bar to be equal to the 4th bar. Sounds really simple, It's extremely hard. Why? Because it's a Markov sequence. You don't know how many notes you have in the first bar. You can define the first bar as all the notes from 1 to I don't know what that fall into those boundaries, the sum of duration meter. From the bit 1 to 5, I want this, whatever the subsequence here, to be the same than from bit 12 to 17, But I want the whole thing to be a Markov sequence. So this is very hard. So we have a solution for that, but there is no bounded complexity called Allen meter. But in that case, as you said, you explicitly impose a structure, But it's already a very difficult problem. I mean, it's very interesting that, and it's very well defined. Basically you want to generate a sequence of integers, and what you say that, and you do all the partial sums, and you say from partial sums this to that, I want to have the same integer, and from partial sum that to something else, So it's really very hard. It's very hard because you don't have a direct relation between the index of an event and its metrical position. So you have to maintain that. This is the first answer, but it's kind of top-heavy, as we said, because you impose a structure yourself. But the other approach is what I was saying was with 1 over f is try to enforce some more general distributions of values or structure using more universal laws. And I can send you the paper we did on 1 over f. I think it's very interesting. It's very nice. It's very nice because in the end it's extremely simple. And so you do this very simple trick to favor let's say some kind of repetitions, and you can see structure occurring. And you don't know exactly when and how and where, but you have this basic property enforced. So I think there are different approaches to that. Is there an explicit one which is already quite hard, or a more like bottom one where you try to satisfy basic universal laws?
Okay, just one question by myself to finish. There is some question about the meaning and the fact that you can invent a style, you can do something like that. And I know that you work on something. Maybe you can say something. You explained to me that you could try to invent a kind of Turing test for the music. That is, then we submit the music, and then we try to understand if the music has been made by a human or by a computer. We can imagine to do things like that for text. Do you still work on that? Do you want to say something?
So the Turing test is a bit like the question on meaning and all that. It's something we try to avoid. So there was a very interesting workshop at AAAI this year, as you may know, organized by Francesca Rossi, about the new Turing test. Because basically the idea that what you say is not adapted to music. Because if I play music, without any context, is done by a machine, is done by a man, doesn't make any difference. I mean, most of the music is actually already more or less done by machines. So a real Turing test has to be a bit different. It has to be kind of interactive, like in the original Turing test, someone is asking a question and then the guy is seeing whether, you know, there is a memory, a context, and all that. So a good Turing test would be rather than, okay, you say, this is a new song, you compose a song, or give us a new song, please do it right away, do an accompaniment or whatever that fits with my song. So there is, I think the interactive dimension is essential for the Turing test. But to be honest, this is a subject which is heavily debated in the community of, what they call this, computational creativity. And there were studies which are very interesting where they played stuff composed by humans and stuff composed by machines to people asking to rate them, you know, what do you like and that kind of thing. And of course they cheat at some point and they discover that there is a very strong bias against machine-generated music, even when it's not the case. So the fact that you know something about how it was generated already, I mean, destroys all possibility of knowing exactly what's going on. So it's a very tricky question. Very tricky. And in my case, I'm not, I don't know what to do there. I'm not really interested. I'm more interested in tools where you, the one guy, you know, finds and gets things that are really interesting for him.